My name is Oliver Van Kijk. I'll be your chair for this session. So we have 5 papers and 1 poster in the session. So we are getting to the end of the conference, so I'm sure you are familiar with the format now, right? We'll have the 5 presentations in sequence, and at the end you get to ask questions to the authors of the papers and the poster during the interactive session, right? So maybe before we start, let me just introduce the poster to you so you're aware. We have a poster called Reassemble by Packing Path-Valid Spectral Placement for 3D Fragment Assembly by Vinicius Hirono Gonçalves and Paula Dornhofer Paro Costa. So you can basically see the poster at the interactive session, talk to Vinicius, who is here. Okay. So then let's go to the first presentation. So first presentation is called PrimitiveAnything, Human-Crafted 3D Primitive Assembly Generation with Auto-Regressive Transformer. And the authors are Jingwen Ye, Yuze He, Yanning Zhou, Yiqing Zhu, Kaiwen Xiao, Yongjing Liu, Wei Yang, and Xiao Han. So unfortunately, the authors couldn't be present here, so they sent us a video which will be played.
Hello everyone, I'm Yuze He, a PhD student from Tsinghua University. I'm happy to present our work, PrimitiveAnything, Human-Crafted 3D Primitive Assembly Generation with Auto-Regressive Transformer here. This work focuses on decomposing 3D objects into building block-like primitives like cuboids, cylinders, and spheres. Let me introduce the concept of shape primitive abstraction. While these terms might sound complex, it's essentially about breaking down intricate 3D objects into simple geometric building blocks like cubes, cylinders, and ellipsoids, similar to how humans use blocks to recreate objects. This approach mimics human perception by transforming general 3D objects into more interpretable, structured representations. As demonstrated by the chair and Mickey Mouse examples on the right, both can be decomposed into collections of cuboids, elliptical cylinders, and ellipsoids. For the characteristics of this task, first it should align with human perception, learning human construction patterns. Second, it needs geometry fidelity, balancing simplicity with accurate reconstruction. So what's the applications? These include robotics, CAD, and interactive modeling. By converting 3D objects into simple primitive combinations, 3D editing and structural adjustments become much easier, no longer something only professional modelers can do. This opens possibilities for user-generated content field, or UGC for short, particularly games where users create content. Let's first look at early learning-based work. First is the CVPR 2017, which first used CNN for shape primitive abstraction but only support cuboids. It also introduced probability attributes, enabling the network to dynamically adjust the number of cuboids. However, as we can see from the results, these methods' reconstruction fidelity is actually quite low, and cuboids have limited expressive capability, making it difficult to model more complex shapes. Next is superquadrics revisited from CVPR 2019, which introduced superquadrics, overcoming cuboid limitations. As shown in the bottom right, superquadrics can achieve a series of 3D shapes through their parameters, handling objects like airplanes that cuboids cannot represent adequately. However, the parametric expressive capability is still constrained by mathematical forms and doesn't support arbitrary types of primitives, which limits extensibility. Moreover, it only supports category-specific training like chair or car models without cross-category generalization and generates limited primitive numbers. Now let's look at how two-reason optimization-based works address this problem. First is EMS from CVPR 2022, using superquadrics-based optimization without training. However, as we can see from the upper right figure, it first fits one primitive as the main body, then hierarchically adds primitives to uncover areas, limiting fine-grained modeling, sometimes modeling complex objects as a single large block. Then there's margin primitives from CVPR 2023, which can achieve more fine-grained modeling. It uses connectivity margin to detect where primitives are needed in the SDF domain, then optimizes primitive parameters in the voxel domain for better local geometry conformance. While these can fit geometry counters, it often leads to overlapping or even coinciding primitives, which doesn't align with human perception. So let's look at how our PrimitiveAnything work achieves the generation of 3D primitive representations that align with human perception for any given 3D content. First, we create a dataset containing original 3D meshes and corresponding manually annotated primitives that align with human perception, totaling 120,000 samples. Based on these, we design a primitive parameterization scheme. For a series of predefined standard-sized geometry primitives, we establish parameters including class labels and rigid transformation parameters for scaling, rotation, and translation. However, these parameterization alone is insufficient. Primitives commonly used in modeling, such as cubes and cylinders, have significant symmetries that lead to non-unique parameters for the same state, which is very unfavorable for deep learning. Consider this cuboid example. First, look at the cuboid in the middle. When it rotates 180 degrees, it completely overlaps with the original. Then look at the cuboid on the right. After rotating 90 degrees and then swapping to coordinate axis, it completely overlaps again. We can see that this problem of multiple parameters corresponding to the same state cannot be solved by changing the parameterization. To address this issue, we propose an ambiguity-free scheme that constructs symmetry sets to identify all equivalent states and determines unique primitive parameters through minimum sum selection. This parameter ambiguity elimination mechanism applies to all types of primitives. The formulas might seem somehow abstract, so let me explain it specifically. First, find all rotation axes of the current primitive and their rotation order. If rotating by a certain angle achieves complete overlap by swapping to coordinate axis, we count these in the rotation order. For example, a 2, 3, 4 cuboid has a rotation order of 2 for the shown axis, but since 90-degree and 270-degree rotations also achieve overlap through coordinate swapping, we count these axes as order of 4. We construct a rotation symmetry set R based on this count. For each rotation case in the set, we compose it with original transformation, then look at all rotation parameters of their composition and select one with the minimum sum as the final primitive transform attributes. This ensures unique parameters for any primitive under any rotation state, regardless of rotation representation method like Euler angles, quaternions, or rotation vectors. Next is the training of the autoregressive primitive generation network. We first convert each primitive attributes, including class labels, rotation, scaling, and translation, into embeddings. During training, we first sample the original mesh surface to obtain point clouds as input conditions, which are processed by a shape encoder to get shape tokens. Simultaneously, we use a primitive encoder to project primitive attributes into tokens. The two parts of tokens are concatenated into a sequence and input into an autoregressive transformer for predicting subsequent primitive features. These features output probability distributions for various attributes through a cascaded decoder. This decoder adopts a progressive prediction structure. It first predicts class labels, then concatenates the class label embeddings with features, and sequentially predicts and concatenates to obtain translations, rotations, and scales, supervised by manually annotated primitive attributes. This design also aims to align with human-crafted patterns. First select primitives, then place it, then adjust angles, and finally adjust sizes. By converting shape primitive abstraction into an autoregressive sequence generation task, our PrimitiveAnything achieves primitive decomposition capabilities that align with human perception. Looking at the experiments, EMS and marching primitives are both optimization-based methods. Actually, marching primitives achieves decent out-counter reconstructions through fine-grained marching and continuous optimization, with primitives often overlap, misaligning with human perception. Our method outperforms their in patterns, reconstruction fidelity, and primitive counts, while showing good generalization on unseen data like observers. In terms of quantitative metrics, we tested on our proposed human prim dataset and ShapeNet, comparing with both optimization-based methods and early category pre-trained methods across 4 3D geometry matrices. The results clearly demonstrate the superiority of our method. Beyond geometries, we also tested segmentation matrix to evaluate the alignment between predictions and human perception. We sample point clouds from predictions and project them onto ground truth meshes, then calculate instant segmentation matrix. The result shows our method has considerable advantages. We also conduct ablations which show that ambiguity-free parameterization can effectively eliminate mode confusion, as clearly reflected in the voxel IOU matrix. Cascaded decoding can increase stability and suppress the generation probability of outliers, as seen in the Hausdorff distance. The chamfer distance loss can enhance detail control. Our method can also be combined with works like Trillis and generated 3D objects from image or text to create primitive-based customized 3D content. As you can see, the generalization capability is quite good. It performs well even on previously unseen data generated by these 3D generation frameworks. That's all for my presentation. Thank you all for listening. Below are the links to our project page, code, and online graduate demo.
Yes, thank you.